you. I'm so glad we found it. Right? I was scared to panic. Man, I never lose anything. I know, I was like, I put it in, what happened?
Are you Cheyenne? Remind me what your name's here. Good, Emma. What are your names again? I'm Shelby. Yeah, I need to get you a quiz. What place is the welcome assignment? Yeah, I was thinking about that. I was trying to find a copy of the quiz, otherwise I have to print another one.
Okay, thank you. I did track me. I did email you, did you get that?
Yeah, I saw your email. I thought I'd responded to your email. I don't check the Blackboard messages though. Oh yeah, that's, turn file can go over there. Let's try to hand back file. Oh, I found a welcome assignment, perfect. So yeah, you can just do that. Not really.
Is this stuff that we got in class?
Yes, you should have gotten that. right, let's go ahead and get started. So kind of the next two chapters, we'll be talking about, the periodic table. We'll start getting into atomic structure, electronic structure. And so just ask questions. That's always a big thing, right? Ask questions. We're kind of, again, we're trying to learn a new language almost. And if you don't have, all the fundamentals, you don't understand what I'm saying, just ask so I can clarify. And so now we're kind of back to where we were the first week. And we're just kind of reminding ourselves what an element was. And so we're just defining our element as a pure substance that cannot be broken down. And again, it's something that we find on the periodic table. And so elements 1 through 88 are naturally occurring. And then afterwards, they are synthetic, so they're made through nuclear reactions. And again, we'll keep kind of having these tours of the periodic table. And so some elements that we might want to be familiar with, just because they're in our body. So of course, we're primarily oxygen. So our body is mainly made up of water. And so of course, right, a lot of oxygen molecules and H2O. And then of course, we're also carbon-based life forms, which we'll kind of get into as we talk about, again, the atomic structure. And then of course, with that, we're also hydrogen and some nitrogen and then other trace elements. And so down here are the other trace elements. Of course, you need like calcium and magnesium. So you need these cations to kind of help transfer your electrons in your body and help with different processes. So like your electrical synapses depend on having magnesium. And so have you ever gotten like a leg cramp? I'm sure you've gotten a leg cramp. And so, right, magnesium deficiency could be a reason why you get leg cramps, or potassium, right? So any one of those kind of ions. Again, you need ions in your body. So that's why they say like, oh, eat a banana. And so you can replace your potassium. And then there are other metals under here that are essential that aren't really listed. So of course we need some iron, and we probably have trace like nickel, cobalt, other metals in there that you may not expect. And so compounds, we mentioned those were a defined chemical formula. And we also have different ways to represent our compounds. So this is more a space filling model, and then we have little colors to indicate. So in this case, red is usually oxygen, and so this is just water that's shown here. And so we could rewrite it in this form. And again, just kind of appreciating right now the structure. So we still have to get into it and the shape and all that and how we got to there. So we haven't really answered that, right? So don't panic yet. And so this is ethane. So the black balls represent carbon, and then the white ones, just like we saw in this one, are hydrogen. And so we can rewrite this one in another form so we can tell what's what. And so something that you also want to be able to do is convert structures to formulas. And so let's look at this one. And so you'd want to be able to write the formula. Let's look at another one first before we look at this tricky one. And so let's look at benzene, actually. And so this is how you draw benzene out. And so again, you want to be able to determine the formula. And so a couple of things that we need to clarify. So carbon always makes 4 bonds. This is slightly starting to touch on, again, why we're carbon-based life forms, but eventually we have to tease out carbon versus silicon. But okay, carbon makes 4 bonds. And then in this structure, so every point is a carbon. So carbon, 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 carbon. So now I'm going to redraw it in another form that's more explicit. So first, I'm just drawing my carbon structure. And then notice it has these double bonds. And so they alternate like so. You can also draw it. So benzene's kind of a weird molecule. It's just called aromatic. And so sometimes you see it drawn like this. And so this means delocalized electrons with this double bond pattern. And so just like we can draw them around here, we could move the double bond. Yeah.
What's delocalized?
So delocalized means that these electrons can go all the way around the ring here. And so that's what leads to the stability. And so for your purposes, what that means is that double bond can move round and around. So, right, I drew it between this carbon, but we could move it over. And so it's just the alternating carbon. So notice it goes double bond, single bond, double bond, single bond. And it doesn't matter, again, which is which, because really what it is with delocalized is they're all evenly distributed, and we would average this to about 1.5 bonds each. So that's what it means by delocalized. Yeah, they would be covalent bonds.
And that's one of the reasons why the electrons are delocalized?
Yeah, because they're sharing. Yeah, it's more with the pi system, but we probably don't want to go too deep into the delocalization. But it's more from their pi system, but we can kind of hold that in our brain. But then we haven't finished drawing benzene. And so, right, I said, well, carbon always makes 4 bonds. And so what the trick is with organic chemistry is that they never draw the hydrogens attached to the carbons. Sometimes they do if they're trying to show stereochemistry, but usually they leave off the hydrogens. And so now we need to add, so notice if we take one carbon, so it has 1, 2, 3 bonds, but oh, we need 4. So from that we know we have to have 1 hydrogen there. And so that means we have to have 1 hydrogen on every carbon, right, since they all have 3 bonds. And I'm just drawing it over here as well, depending, again, where you put your structure, your double bonds. So that's benzene. And then we can finally write our formula. So C6H6, so 1, 2, 3, 4, 5, 6 carbons, and then 1, 2, 3, 4, 5, 6 hydrogens. So now go ahead and try to write the formula for this molecule here. And I will give a hint, right? So this is a little methyl group hanging off of here. So there's a carbon at that point. And think about what has to be attached to that carbon. So I'll let you try this out, and then I'll draw it more explicitly for y'all.
certain elements come before other ones?
It usually it's carbon, hydrogen, and then alphabetical order. But yeah, it doesn't matter as much. We just want to get our total counts. Now I've gone ahead and redrawn our structure so we can see kind of what's what. And I'm still kind of filling in the hydrogens though, so there was no hydrogen there. You could also look at this structure drawn, so I'm going to highlight, right, all our carbons. So there's a carbon there. This has to be a carbon, carbon, carbon. So all these are carbons. And so, right, don't forget this point. So if this is a carbon, it has one bond. So then it has an H3 attached to it. So I drew that over here on all those little sticks for our methyl group. All right, so then count them up. How many carbons do we get? I get 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. And if you need to number them, you can, because, again, this is relatively simple. So on an exam, you might see like a bigger molecule, so you can always label them, right? 1, 2, 3, 4, 5, 6, 7, 8. So C8. And then how many hydrogens do we have? So this one is tricky. So you want to look at your structure, and then you have to look at every carbon, make sure that it has 4 bonds. So this nitrogen with the little stick off of it, so our methyl group, I drew over here, so CH3 to complete our 4 bonds. This carbon, right, notice it has 1, 2, 3 bonds, so I added a hydrogen there. And then don't worry about the other atoms. So like if the nitrogen has a hydrogen on it, it has to be drawn out for you. This carbon already has 4 bonds, so that's fine. I put our CH3 there. This carbon has 4 bonds. This carbon we already fixed. This one has 4. This one has 4. So then how many hydrogens do we have? What do we get? 10. Do other people get that? Yes, no? Are we confused? So write 10 hydrogens. Excellent. So write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's kind of shown better on this picture. And then the rest we can just count up. So how many nitrogens do we have?
4.
So 4, so that's nice and easy. How many oxygens? 2. 2. So there's our formula. Yeah.
How are we supposed to know like where the carbons are at? It's not like I don't know.
So Yeah, anywhere that there's a point or an end point, that's a carbon. So the carbons are always unlabeled. So like every other atom's going to be labeled. Yeah.
Wouldn't the carbon that you have labeled 3
Oh.
also have an H3?
This one, 3?
The one attached to the nitrogen on the right side. I don't know where you're.
Yeah, I have 1, 2, 3. This is carbon 3.
So not like the technical carbon 3, but the one that. Oh, actually it's 7. Sorry,
Oh, this one's
yeah.
7.
Wouldn't that be an H3 as well to make 4 bonds?
Yeah, so it's CH3. So I have it written here as CH3 on this one. Okay. Yeah, I just didn't write it over here. I can do that.
So if there's like a carbon with only like 3 or whatever, it's always going to be hydrogen on
Yeah. Yeah, so you never have just a lone.
Is there ever more than just 4?
Nah.
Okay.
So let's try another one. Oh my gosh, what was that? All right, so try this molecule. Oh my gosh, what is going on? All right, try that molecule, see if you can determine the formula. Mm-hmm.
I learned in bio class last term, when you're counting carbons, that you start from the oxygen and then you count that's the first carbon to the right of that. As just a way to count, okay, this is the first carbon, second carbon, third carbon. But there's no oxygen, is there a rule around that?
No, I mean, I would just label the carbons, yeah. All right, how's our formula going? And so, right, all these are carbon, so carbon, 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 carbon. And so we need to attach some hydrogens on there since they're missing 4 bonds. And of course, this carbon has 4 bonds. We have a carbon here, so hydrogen, hydrogen. Carbon here, so 1, 2, 3. This is a tricky one, so don't forget that hydrogen. And CH3, CH3. So then, how many carbons do we count?
I counted 10.
So I hear 10. Is that what other people got? So I see some nods. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then how many hydrogens? So don't forget the one attached to the nitrogen either.
14.
14. I might double check that because make sure you didn't miss that one. Let's see. So 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15 on the nitrogen. So I'm going to skip that. And then 1 nitrogen, and usually you don't put the 1, you just leave it as N if there's just 1 nitrogen there. So implied 1 subscript. How do we feel about that one?
So the H being there, does that change anything? Or like if it wasn't there, would we put a carbon? Or?
This H right here?
Yep.
So the only difference is that they show the hydrogens explicitly attached to the nitrogen. So if it was missing it, it just like wouldn't really make sense, or you would have a weird structure.
Okay.
Yeah, but they have to draw it in like for you, or if you were drawing this, right, you'd want to draw the hydrogens on the nitrogen. So it's just a carbon where you can leave off hydrogens. Here, let's try another one. I'm just trying to find a nice drug I like. Oh, I misspelled the drug I'm wanting. Let's do this one. Okay, we'll try this one, and I'll try to find another one that doesn't have so many benzene rings. So how are we doing on this one? How many carbons do we get?
16.
16? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So see 17, how many hydrogens? This one was tricky. So I think it's 18. So make sure you didn't forget the one attached to the nitrogen. And then draw in all the others that are attached to the carbon. So this one has 4 bonds, but then this one 1, 2, 3. So kind of tricky there. And then 2 on each of these. This is a methyl group. So let's see. So 1, 2, 3, 4. And I'll do the ring. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then I forgot 18 on that one. And then, of course, how many fluorines? 3. How many nitrogens? 1, so we can leave that like so. And then oxygens? Excellent. So there's our formula. And so this is fluorextine, or you probably know it by Prozac. Some of those fun facts. This was meth, by the way, methamphetamine. And that is the methyl group. And so if you take that off, right, that's just amphetamine there with an H. And the methyl group allows for better crossing of that blood-brain barrier. And then Prozac has this little group, so these fluorines also allow for better blood-brain barrier crossing. So you see a lot of fluorines in drugs. Yeah, fluorextine. That's just its name. Since this name doesn't correspond to like the chemical name, but we won't get into chemical naming. That's more for like OChem. We'll get into like simpler naming. All right, so that's at least a preview of how to kind of interpret these structures. And so we might go back to this, and this will come up. But now we want to talk about atomic structure. So now we want to kind of back up and kind of define, well, how do we get our elements, right? Why do we have elements on the periodic table? What are they made out of? So now that's where we're going next, so looking at our individual atom. And so this is important. So now it says that atoms are composed of subatomic particles, so protons, neutrons, and electrons. And so the significance is, so the mass of the proton and the neutron are the ones that kind of dictate the mass of our atom. And so if we look at our mass of the electron, so it's on the order of to the negative 31 kilograms versus the proton and the neutron are negative 27. So usually we say that the mass of the electron is negligible. And we have a chart coming up that kind of gives a better summary. And then our protons, so they are assigned as a formally positive charge, and then electrons would be formally negative. So they're opposite charges is kind of the importance there. And then the neutron has no charge. It does have mass. And so this is a good summary. And so often we say that the proton and the neutron are about 1 AMU, so we kind of ignore the last part. And then we say the electron is negligible. So again, it's 0.00055 AMU. So we just kind of ignore it when totaling up our masses. And then again, there's our relative charges. And of course, Millikan's oil drop experiment is what determined the charge of an electron. So he was pretty accurate, which is pretty amazing given the equipment of the time. And so again, we have our absolute masses, but this is going to be kind of important for our uses, so the AMU. And so now this is telling us, well, what defines an element? And so this is important. So it's defined by their number of protons. And so if you change the number of protons, right, you change the identity of an element. And again, that only happens in like nuclear reactions. Don't really talk about that a lot. And so again, right, the number of protons defines the element. I can't emphasize that enough. And so our protons corresponds to the atomic number, and formally it's given by the symbol Z. So if you see them asking for Z in your homework, that's what they want. And so let's kind of start to unpack a few things. So we have, right, helium. And so now we're looking at the nucleus. So the nucleus contains protons and neutrons. And what's highlighted here, so they put 2 protons in the nucleus. And so now we can see how that corresponds to our periodic table. So if we look at our periodic table, we have our upper number here. So that's our number of protons and also our atomic number. And of course, you have your periodic table with the chart. And so if we go over to helium, so we were looking at helium on this little drawing. So if we look at our periodic table and compare, so helium, there's 2 protons corresponding to its identity. And then we'll start talking about this mass number. So this mass here is an average of all the isotopic abundance, which I'm kind of jumping ahead, but we'll kind of come back to that. But the key point is, so it's about 4, so about 4 AMU. And so that means that if it has 2 protons, and we said, well, the electrons were negligible, so that means it has 2 neutrons, again, on average, to give us 2, 4. And so that's why they put 2 little blue balls here to show our neutrons. And then now we're looking at the carbon nucleus for comparison. And so that one, they have 6 protons in there, so you can see 6 red balls, 1, 2, 3, 4, 5, 6. And again, just so we're all on the same page, so carbon 6 here. And so we won't quite get into the mass. So the mass is a little off, but carbon 12 is our most abundant isotope. And again, I'm kind of getting into other terminology, which we'll get into. But basically, if we want to get into make an atom of carbon 12, it has to have 6 neutrons. And so that's what's depicted here. 1, 2, 3, 4, 5, 6 neutrons in our nucleus. So that's what is shown there. And so, of course, elements are arranged in the periodic table by their atomic number. And so we can start looking at our periodic table. So we'll take a few tours of the periodic table. And so, of course, you can see they go in increasing numerical order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 11, 12, 13, 14, 15, 16, 17, 18, and so forth. And so that's just increasing order, but we haven't gotten into, right, all their families. So that's kind of coming. And so we'll find that elements within the same column have very similar properties. So those are its families. But again, we're going to come back to this idea in just a second. And so then here is our introduction to isotopes. So elements with different number of neutrons. And so now we're saying, so all atoms of a given element have the same number of protons, except they may have different number of neutrons. And so this is just a naturally occurring phenomenon. So scientists don't have all the answers as to why these isotopes exist. But basically it comes down to kind of a ratio, and we'll kind of see that. And so if we look, so we have 3 different isotopes of neon that exist, and they all have 10 protons. So right, they all have the same number here. If we need to double check ourselves, so we look over, so neon, right, atomic number 10. And then our different masses tell us, again, how many neutrons they have. And so we could write out our little chart here. So if we have neon 20, so we can do protons, neutrons, and let's put in electrons there. So neon 20, how many protons does it have? So how many protons? What's its atomic number?
10.
So 10. And then our big number here is our mass. And so if you need to write this down, so our total mass for each atom is equal to neutrons plus protons. So I just kind of abbreviated. And so how many neutrons do we have?
10.
So 10. And then so for electrons, let's write our formula. So the way I like to think about it is, so we said electrons are negative. So if you treat them as negative, that means that your charge, right, is equal to protons plus electrons, again, if you're adding them as a negative. So that's kind of the best way to think about it. And so in this case, we have no charge, so we haven't gotten into that. So then how many electrons do we have? 10, exactly.
So could you look on the periodic table and the little numbers on the bottom?
So which numbers?
Oh, sorry, it's not right there. It's on this one though. It has like it shows how many electrons are in the rings, so like 2, 6 or 2.
Oh yeah. So you're looking at. Let me pull up another periodic table because I think I know what you're talking about. If I can find it. So does yours just say 2 and 8 on the bottom? Yeah, so those numbers that you're looking at, so that corresponds more, so if we're looking at neon, and then you see sorry, I can't like move my cursor. You see how it has 2 and 8 there as well? So that corresponds to how many electrons it has in each energy level. So if you add the total number up, that gives you your electrons for neutral neon. Does that make sense? So now going back to our isotopes. So now if we look at neon 21, so how many protons does neon 21 have?
10.
How many neutrons?
11.
11. And then how many electrons? It's still neutral.
So it's still 10.
So it's still 10, exactly. Trying to make sure y'all are awake. And so now if we look at neon 22, how many protons?
10.
How many neutrons? 12. And then how many electrons? 10. Excellent.
So will it always have the same amount of electrons, even if it has more
Yeah.
Okay.
So, yeah, unless I do something like, so we'll get into ions after we finish isotopes. But yeah, I didn't show any charges on here, so we can just assume they're neutral, so we'd have the same amount of electrons as protons. And so there's different ways to represent our isotope. So this is kind of the most common with the mass number on top. And you might just see this, so right, you might see like carbon 14, for instance. So this is another isotope. Does anybody know what carbon 14 is used for? So we have 3 common isotopes of carbon. So carbon 12 is just kind of the normal one that's not radioactive. And so, right, it has 6 protons, 6 neutrons. And so this is what I was kind of saying, is that it tends to be when they're equal, they're stable. And so carbon 13 has about a 1% abundance. And so this is used for C13 NMR, which probably doesn't make a lot of sense to y'all. But basically it gives us a pretty picture of the molecule, and we'll kind of leave that as such. And it's NMR active, and so it's the only one that's NMR active, which means that it can be influenced by a magnetic field. And so this would have 6 protons, 7 neutrons. And so no guesses for carbon 14, what it's used for? So this is used for carbon dating. So right, so radioactive dating. So carbon 14 has a half-life of about 5,730 or so, if I remember. I'd have to look up the exact value. And so it has 6 protons and 8 neutrons. And again, just with that unevenness, now that means that it's less stable in our nucleus and it's radioactive. So again, it's hard to predict who's radioactive, but just as they tend to get more imbalanced, that's when it's radioactive. But again, scientists can't fully predict why things are radioactive. We just kind of observe this phenomenon. And so again, here's one way to write it. So sometimes they have the atomic number there, or we may not see it. So again, this is another common abbreviation. You may also see it represented like so, where it's kind of written off to the side. So just kind of be aware of that. So you could write it like that. So that the total mass would be written to the side. So neon 20, so that corresponds to the total mass. And then if you had to calculate, of course, right, the number of neutrons, you can always go back to the periodic table, remind yourself of how many protons it has, the atomic number, and then you can figure out the neutrons. All right, so try to write this one out. So what's your atomic symbol? Your mass, atomic number, mass number, and symbol of a chlorine isotope with 18 neutrons. so what's our symbol looking like? So what's our atomic number for chlorine? How do we find that out? So 17, and again, right, if you didn't know, which I don't expect y'all to have anything memorized, but right, look at your periodic table, so 17, so excellent, so we have chlorine, 17 on the bottom, and then what's my total mass?
25.
Oh, yeah, double check that, yeah, forgot to carry the 1 over, but 35 looks good. So yeah, we have 35 chlorine there.
What's the atomic number? It's 17. Does that mean it has 17 electrons?
Yeah, so then it would have 17 electrons, 17 protons. And so we haven't gotten into ions, but we'll do that right now. But so what I normally do with my classes is we take like a little break since, you know, it's a 2-hour lecture. So we're probably going to go ahead and take a quick break. So probably reconvene in about 10 minutes, so about 2 o'clock. And then we'll continue back, so then we'll talk about ions in a second, which is where y'all are ready to go brain-wise. So yeah, take a little break, and we'll be back. Go to the bathroom. Where'd your classmate go? Digging left right as I was going to start. All right, let's start getting back into it. And so y'all keep kind of asking about ions, or at least that seems to be on your mind unintentionally. And so now let's talk about what ions are. And so ion refers to just any charged particle, or in this case, we're looking at elements, so any charged element. So it could also be a compound, but we'll get into that again as we kind of progress in our course. And so we can have, more specifically, a cation. And so I'll rewrite cation, but put a little plus sign so you can kind of remember, if you see that T is a plus sign, so cation, so something that is positively charged. So meaning it lost an electron. And so let's try kind of what we were doing before, but a little bit different. Let me make sure. Oh, I picked the wrong. That wouldn't make sense. So let's try 40K, but what happens if I put a little plus sign next to it? So now see if you can figure out, so protons, neutrons, and electrons. So what is this telling us? Yeah.
Definition of ions is any charged atom.
Any charged either element or particle, because it could be a compound, because later we'll see polyatomic ions, but right now we're just looking at like elements more specifically. And so looking at this, so not trying to rush y'all, but trying to also look at it together. So we're looking at potassium, so element 19. So how many protons does potassium have?
21.
Oh, check that again. Because remember, it corresponds to its atomic number. For protons? Remember, it's atomic number, so it's whatever number is on the periodic table.
Oh, 19.
So 19. And so, right, if 40 is its total mass, so protons plus neutrons, so how many neutrons does it have?
21.
So that's 21. And then did we figure out what our electrons meant? So, right, we have a plus charge here. And so if we go back to this formula that I had kind of given, right, so I said that our charge was adding our protons plus our electrons, but again, adding electrons negatively. So you can kind of do the math. So if you have a +1 charge, you have 19 protons, and then you want to add, so minus so many electrons, so plus negative electrons. So from here, we can see that, oh, my number of electrons is 18. Or what some people like to do is, okay, let's start at the neutral, right? If we're looking at neutral potassium, well, that has 19 protons. And then if it's +1, that means that we had to have lost an electron. And so that would mean we have one less electron than protons, giving us 18 again. So kind of whatever way you see that best. So let's try another one. And so what would it be for calcium? 43. So again, try that out again. Protons, neutrons, electrons. So take a minute. So how many protons do we get for calcium? So 20, and again, right, that's straight from our periodic table. So 20, and then how many neutrons did we get? So 23, so excellent, right? 43 minus 20. And then how many electrons we could compare with our protons? So 18 electrons, excellent. And so maybe it's easier to start at the neutral and then, okay, we have +2, so we had to lose 2 electrons since they're negative to give us 18. We could do the math, right? Protons, so adding in 20 plus negative 18 gives us 2 plus as well. And so, right, we can also have negatively charged ions. And so those are called anions. So now these would be negatively charged. And again, we're looking at elements right now, but they could be polyatomic ions, or so that can be any charged substance. And so now let's try another one. So let's see. So what if I have chlorine 36 with a -1 charge? So same thing, so I'll rewrite it. So protons, neutrons, electrons. How many does it have? I'll put another one. So there's sulfur 34 as well with a 2- charge. So you can work on those two. So what do we get for protons for chlorine 36? Yeah. So 17 protons. And again, that should be from our periodic table. So 17. How many neutrons? 18? 19. 19 neutrons. Just double check your math on that one. So if we're adding up, right, protons plus neutrons have to give our mass. Yeah, so it could have been a small error. I'll just show it on the calculator. And then how many electrons? 18. So right, comparing to the neutrals, of course, if it was neutral, it would have 17, but we have one more now, so we have 18. And then you could set up the algebra So -1 is equal to, so 17 minus my electrons. And so then that gives us 18 for our electrons again. All right, what about sulfur? How many protons? 16. How many neutrons? 18. How many electrons? 18. So again, comparing to our number of protons, we have a -2 charge, so now we need 2 more electrons. Excellent. Questions on that so far? And so now we're going to kind of start our tour of the periodic table. And so this, we'll start off with kind of fun facts, but probably get into electronic structure as well. And so this is a good periodic table as well to look at. So this is just ptable.com. And then you can click these buttons up top and they give you extra information. So normally I just like looking at this properties button. And what I usually like is it shows you kind of some Wikipedia stuff, although it used to be cooler. And there we go. So we can see, so let's start off with our tour. And so, right, we had said that they're arranged in increasing atomic number, but then they're also in these columns, right, of their families. And so if we start over here, so this is our group 1 alkali metals. And so we might want to write that on our periodic table. So our alkali metals, although it should be on your periodic table somewhere. So it depends kind of which one you're looking at. So this one has a more detailed key, the version that I have up here. So it has our alkali metals all in pink. And so maybe I'll bring in some metal for Wednesday to look at. Because what's fun is, of course, they have increasing reactivity as they go down. So if we look at lithium, so lithium is a nice shiny metal piece. It's pretty soft, so you can cut it with like a razor blade. So all these are relatively soft. And then notice how it's stored in oil, so it should be stored in mineral oil. And that's because it reacts with water, so it reacts with water to make lithium hydroxide and H2 gas. And again, I'll bring in some sodium on Wednesday, or lithium, sodium, potassium. And so as we go down, so sodium gets more reactive. And again, it's the same thing, kind of silvery, shiny, very soft. And then potassium. So potassium, again, has to be stored under oil. And this is the last one that you can work with in air. So past that, so rubidium, cesium are both too explosive. So rubidium is always in an ampule. And if you look up YouTube videos, you can see like people basically opening the ampule by some mechanism and it explodes pretty much immediately. So same thing with cesium. So that's also very, very, very water reactive. And so again, stored in a sealed ampule or in a glove box or something. You probably wouldn't need to use it. And then francium is radioactive, so just keep that in mind. It's still there, but yeah, very radioactive. And they don't even have a picture of francium.
So what is I didn't know like potassium nitrate is like a step remover or something, and like it is also like used like for as an oxidizer So what does the nitrate mean? Like,
So nitrate refers to a polyatomic. So nitrate is NO3 specifically with a charge on it. So then we'd have to draw it out. Yeah, so that's nitrate and what it looks like.
so why does that like make it not explosive?
So you mean like why is lithium nitrate not explosive?
Yeah, I'm just like, because like potassium, like you can make rockets is what like it's an oxidizing potassium nitrate, but it doesn't explode or something, is that right?
So I guess, so you're asking about potassium nitrate specifically?
Or just any, like what does the nitrate mean? Like, what is, I don't know, never mind.
Well, I guess I'm kind of confused what you're asking. So it depends. There's a lot of different things, right? So nitrates can be used as like a fuel, but I have to look up exactly how you convert it, right? Because you can convert nitrate to ammonia. But you don't readily do that.
I think he's asking, you know, when the nitrate is bonded to the lithium, then it's not explosive. So what is the nitrate doing when it's bonded to that to make it not explosive?
I guess I still don't understand because nitrates themselves aren't really explosive, though. So you have to like.
Well, that's what he's saying is the lithium nitrate's not explosive.
I was just wondering like why the lithium goes from explosive to like not explosive.
Right.
So I guess, are you asking about the lithium or the nitrate or the sodium or the potassium?
What's their relationship together? Why is it not explosive once the nitrate gets added to it or bonded to it?
So the problem is I'm still not understanding the question because are you asking why the sodium is not dangerous or why?
I don't know. I'll maybe ask you later. It is confusing. Like, why does sometimes they explode, sometimes they not? Like, just depending on like
The functional group.
Yeah. So the problem is we still have to distinguish right between an element versus because you're talking about polyatomic compounds, right? So when they're potassium nitrate, so potassium nitrate is just like a salt, but then you would have to like do something to it. So because right, nitrates just don't explode, like no nitrates explode. So it doesn't matter whether it's sodium nitrate, lithium nitrate, potassium nitrate, rubidium nitrate. But yeah, because I guess I'm still confused what you were asking, right? Because there's a huge difference, and I don't know if this is going to answer your question, but right, there's a huge difference between like sodium metal, right, and then sodium chloride. So maybe that's part of your question. So again, sodium metal in its elemental form, right, is a nice shiny metal, but then you obviously eat sodium chloride, right? But you cannot eat sodium and you cannot eat chlorine, right? They would both kill you. I don't know if that answered your question necessarily.
kind of, yeah.
Probably has something to do with the process in which it transforms and the nitrate is bonded to it.
Yeah.
Chemical alteration.
Yeah, so that's where we're going. And again, maybe I didn't understand your question. So this is kind of the hard part of chemistry because we're like not talking the same language necessarily. So those are alkali metals. And so let's actually, I'm going to teach it a little differently.
Are you saying alkali or alkaline?
Alkali metals, alkali. So alkaline metals is the next one. So right now I'm just saying alkali metals. And so let's start looking at our electron configuration. So that's kind of this tour is looking at electronic structure, but I want to try to do it together. And again, this is going into chapter 3, so we're going to kind of move slowly. And so let's look at our electronic structure for a second. And so now we're looking at this, and we're starting with kind of our first row here. And so maybe if we go, so you can look at your periodic table as well. So again, it had those little like cryptic numbers beneath them. I'm trying to find my periodic table. Okay, I don't have my copy there. So right, if you look at those little numbers where it says electron configuration, so that's trying to tell you how to fill it up as well. So let's look at the electron tab of this little P table. And so our first row, the first thing we're going to be doing is filling in our S block. So our S block is our alkali metals here and alkaline earth. And so let's, again, we're kind of looking at chapter 3 to help us. And so this is, right, the shape of an S orbital. And so let's also relate this to, so you may have seen kind of the Bohr model is used a lot in like high school chemistry to kind of introduce you to this topic. And right, you have these kind of energy levels, and they're filled up, right? So probably 2, 8, 18, and 36, if I remember correctly. Does this sound familiar to people?
Is it 32?
I would have to calculate it. Yeah, you might be right. I think it's 32. So does this sound familiar to people? All right, so now let's kind of re-understand this, because now we're going to go at a deeper level. And so this first little shell here, this corresponds to our first row of the periodic table. So this is all we're filling up. And so this is our first energy level. And so our first energy level only contains an s orbital. So that's why it only has 2 there. And so again, we're filling up our 1s. It looks like a sphere. There's only 1 s orbital. And so we sometimes also write it by these little lines. And so if I want to say, well, I'm filling up my 1s, so now let's go to electron configuration. And we're going to start with hydrogen. And again, we fill up our 1s orbital. So this is 1s1, with that 1 indicating how many electrons we have. Does that make sense so far? And then, so if we go over, so we'll kind of jump around. So then if we look at helium, so we can fill up helium just because that's self-explanatory. So now for 2 helium, now we have 2 electrons, so now it's 1s2. And so now let's go back to kind of the thoughts of our families. So again, I'm trying to teach this a little differently than I normally do, but this is always a part that kind of starts to lose people. And so we were talking about our alkali metals, and so we'll kind of go back to it. But each row here starts our new energy level. So for example, right, this is 1s. Now lithium would start 2s, sodium's 3s. And so you might want to write this on your periodic table, just all these s's in. It'll become more relevant later as we look at our electronic structure. And so kind of the key and what we're getting at, so we want to explain, well, why does reactivity increase as we go down, right? So we want to answer that. And it's part of our shells being added. And so now what we want to do is kind of see the pattern. So looking at our structure, all of these start, right, with NS1, right? So they have one valence electron. So that's something else that we want to get here. So one valence electron, which we haven't quite defined, but we're kind of, again, dancing around. And so let's look at lithium for a second. So let's write, so see if you can write lithium's electron configuration. You can probably guess it from the hints that I've given. So what do we get for our electron configuration? And so let's look at this. So we said, right, we were filling up our 1s orbital, and then this is still our s block, and I said that this started 2s. And so we might want to highlight this. So this is our s block. So then our lithium electron configuration should be 1s2, 2s1 there. So did we get that? So does that make sense? So we're starting our, again, second energy level here. So we'll get into the P blocks, but I feel like I'm jumping too much. All right, so then we can see, we can define a few things. So 1s2, so this is a core electron. So core electrons are anything that are not the valence, so your valence are just defined as your outermost shell. And so, right, this would be your valence electrons. Again, notice, right, we have one valence electron for lithium. And let's see, so we'll probably come back to the electron configurations of sodium and potassium. So let's look at, let's keep kind of taking a tour. So we just want to get familiar with our elements. And so now going over, so now we can see the next are the alkaline earth metals. So they sound really similar, but not. And so now these are also water reactive, but not as much. So they still kind of react and fizz, but pretty slowly, so less excitably than, of course, the alkali metals. So calcium gives a decent fizz in water. So calcium should be nice and shiny. So I want to say you play with this in lab, if memory serves me correctly. Otherwise, I can pull some out for us to look at some point. And then beryllium and magnesium are less reactive in water. So again, reactivity increases as we go down. But magnesium, so you would need like a little bit of hydrochloric acid for that to go. So again, we'll do that in lab. And so let's just look at other alkaline earth metals. So again, they're all kind of shiny still, a little bit harder than the alkali metals. So there's barium. So again, nice and shiny. And then of course, radium is radioactive. And so let's at least do the electron configuration for beryllium so we can figure that out. It's still in our S block. So see if you can write that down. So what do we get for our electron configuration for beryllium? So 2s1 was lithium. So kind of follow the pattern, right? So we're just adding one electron. So this is ns1. So now this will be ns2, kind of the pattern. So if we go back, right, we were at lithium. So lithium 1s2. And now we're going to fill up that s orbital for 2s2. And then double check yourself. So these superscripts should add up to what how many total electrons we have. So neutral beryllium means we have 4 electrons. And so again, I'll just kind of point out these are our core, and these are our valence electrons. And so again, if you need to write this right to valence electrons. And so you should have little numbers though, right? So that's what these little numbers kind of help you with. So 1 valence electron, 2 valence electrons. We're going to ignore this for now. And then notice, right, it goes to like 3A. So 3 valence electrons, 4, 5, 6, 7, 8. So that pattern will just continue. But we'll go back again slowly over it as we kind of bounce around our periodic table. All right, so let's go back to kind of our tour and again orienting ourselves. And so if we look at this periodic table, so we can kind of take a more general overview. So as we go from left to right, it goes from more metallic to less metallic character. And so we want to at least look at the transition metals. So I said we're going to kind of skip them, and so we will, but we'll at least kind of look at them. So of course, right, this big block in the middle is our transition metals. So that corresponds to our D block, which again we'll kind of circle back to. Let's at least look at the periodic table. And so the D block elements, so they're primarily driven by their D electrons, and so that's what makes them fun, but also awkward to introduce to, again, new students to chemistry, because they have a bunch of exceptions, at least that's how they're thought of. But again, they're mainly all metals, so we can look at them. So let's just look at manganese. So right, they all look like boring metals for the most part. And then once you actually get them into compounds, though, that's where the fun colors come from. So all these transition metals, once they are in complexes, then they give fun colors, or they're also a lot of impurities in like gemstones. So like iron, tends to give like red. Cobalt can be anywhere from like purple to green, kind of depending on the oxidation state. So nickel is usually green or orange. And so, again, lots of fun colors, but we'll kind of come back to them later. And so then we start going over to, this is what I call our P block side, so we'll have to break that down. And so notice, so these are our metalloids over here, and then you may have your periodic table. So this one, for example, this one's a little better because it distinguishes between kind of our basic metals versus our metalloids here. So notice your metalloids are your stair step, kind of separating your metals and your non-metals. So then once you cross over, these are clearly non-metals. And so now let's look at the fun pictures again. And so this one is not clearly showing where the stair step is, so just kind of keep that in mind. I think it's labeled over here maybe. So we have boron, so again looks pretty boring. It's metal, so same thing. Aluminum, of course, right? You've seen aluminum, so aluminum foil is just aluminum really thin. Gallium is pretty fun, so notice gallium is labeled on this one. So this tells you their series. So even though it's not labeled on the stair step, it's labeled there. So notice that, right? So it went from metalloids to post-transition, or just what we can call basic metals, so whatever they're calling it. So gallium melts in your hand. That's a fun one. And then we have indium. And then thallium is toxic, like salts of it are toxic, so you have to be careful. I wouldn't recommend working with thallium, so it can also cause like hair loss if you work with thallium. And again, you were poisoned, so that would not be good. And so then we start moving over to group 4 over here. So again, 4 valence electrons. And so we can look at carbon. So of course carbon is a nice black powder normally, if we're just talking about like carbon or charcoal. You might also see carbon in those forms of like, have you seen those black ice cream cones and stuff? Yeah, so sometimes, and this is like yeah, exactly. And you have to be careful because sometimes they use like a really, really deep like green dye to make it almost black. And I almost say like that's safer because the problem when they use the activated charcoal to give you the black color is some people could be sensitive to that. So do you guys know what activated charcoal or carbon is used for primarily? I don't know if it's abrasive, but it's used as like an absorbent. So sometimes people take like activated charcoal to like help take out whatever toxins or something that they're allergic to. I always caution people about doing that because you don't want to accidentally leach out, essential ions. So we were talking about you need potassium, magnesium. So you don't necessarily want to overdo it on the carbon. So that's kind of like my word of warning. So some people can eat it just fine, but if it does make you a little ill, it's probably because, it's leaching out something and makes you feel weird. So that's kind of the thing about carbon and eating black things. But yeah, it's pretty safe, but like I said, it could make you feel a little weird if you're sensitive. And then, so silicon, notice, it's a metalloid again, so that's used in semiconductors. And well, I guess we won't get into it, the carbon versus silicon-based life form thing yet. And so germanium is again back to being a metalloid. And then tin, so tin metal itself is not toxic, but then tin compounds, again, same thing, tin compounds are highly toxic and can be poisonous and cause seizures, again, if you're working with like tin compounds. Lead is, of course, a heavy metal and can bioaccumulate, so that's not great either. And so then we go on to group 5 over here with our 5 valence electrons. So it has this funny name too, the pictogens. So that's another name for that family. So notice, right, some families have specific names, some don't. I'm not really sure what the rhyme or reason for that is. And so nitrogen, of course, is a gas. And you can, of course, condense it down to liquid nitrogen. So there's some liquid nitrogen, which I'll bring in at some point for your class. And then phosphorus. So, right, we went over phosphorus with our allotropes. So, of course, that is very non-metal in character. So, of course, we've crossed over to non-metal. Arsenic goes back to metalloid, so it's nice and shiny again. Antimony, again, is nice and shiny. And then, of course, bismuth. You like bismuth? And then, so then we look at group 6. So group 6 are formerly called the chalcogens. I call them the smelly family. And so, right, oxygen is not smelly. We breathe that in. And then if we condense down oxygen, so it's actually blue, which is fun. And then sulfur, of course, starts to get smelly. So pure sulfur generally isn't smelly, but like hydrogen sulfide is. And then I was hoping they had a picture of mercaptan. Let me just look it up. So mercaptan. So mercaptan is actually what they put in like the methane gas so that you can smell it and smell that, oh, it's leaking. So it's sulfur-based compound. So pretty smelly. Yeah. And then if you go down, so selenium, if you were to work with compounds of selenium, so they get smelly as well. So these are all smelly. And then tellurium is even smellier. And so you would not want to work with compounds of tellurium. And I think one compound of tellurium, it was being manufactured, and then it caused like an evacuation of the town just because it is so smelly and has like a really bad garlicky odor. And so that's the other problem. So this is also kind of toxic. And so it even says here that if you metabolize it, then you get this nice garlic-like odor, breath. You would not want to experience that, but again, smelly elements, so not good. And polonium, I'm not sure since it's radioactive, so I don't know if anyone's played with its smelliness since it's more radioactive. And then, so looking at our halogens, so halogens are all group 7 over here with our 7 valence electrons. So fluorine is, of course, a gas, and this is condensed down fluorine at liquid temperature. So fluorite, yeah, would be the ion, yeah. Although fluorite, I think you might be referring to like the crystal itself. Yeah, so that, I think that one has a slightly different chemical formula, but still like fluorine base. And then chlorine is a kind of pale green gas. So working with fluorine and chlorine is extremely difficult, so you need like special regulators that are at least somewhat resistant to corrosion, and then of course you have to check them because they will leak. And then bromine is more favorable though to add as a reagent. So bromine comes in a liquid, and it is still an angry fuming liquid, but you can pipette it and work with it. So this is a good reagent in organic chemistry. And then iodine, we have some iodine in lab that you guys will look at for like, your samples. And that's always fun to look at. And so the fun thing about iodine is it sublimates, so it goes from a solid to a gas, and then it will recrystallize in its own container and kind of make shiny new purple crystals on top. And this is also a really good reagent to use unfortunately, because of Breaking Bad and meth production, so it is a great precursor to meth. Well, it's a great precursor to a lot of things, so any synthetic product. But iodine is now also a regulated substance, so even trying to get like liquid iodine that's used for disinfecting can be an issue. But yeah, especially trying to get solid iodine is an issue. And then our last elements are our noble gases, and of course these are relatively unreactive, so all these are gases and they're showing them in their, of course, lit up form. So neon, argon, krypton, which you saw some of these, xenon, and then of course radon is radioactive. So. All right, that's probably a good stopping point. So don't stress out if you're confused on the electron configuration. So we're going to do that again on Wednesday. So kind of re-going over it, kind of re-going over how we fill this in. And then we want to see, right, how electron configuration leads back to reactivities and all these properties we talked about. So that's kind of where we're going. And then hopefully we'll maybe answer your question better over like why you can eat, you know, sodium chloride as opposed to sodium. So hopefully that's where you're going. All right, we'll end here. And then I will see the other half of you in lab on Wednesday, and then I'll see y'all on Wednesday.